Welcome to this class on fluid mechanics, and in today's class we will be discussing what we call our potential flows. Now, as the name indicates, potential flows are flows where velocity potential phi exists. And for this we have seen that velocity can be written as gradient of phi if del cross V or vorticity is equal to 0. But when we talk of potential flows, we impose the incompressibility condition also, which will mean that we are talking of del dot V is 0, and we have seen this in the last lecture. The governing equation then becomes del square phi is equal to 0. Now, for the we have a lot of literature in fluid mechanics where fields have been solved using this equation. But what I'm going to do for the purposes of this course, we will introduce one more assumption. So we already have made the assumption of incompressible and irrotational flows for del square phi to be valid. But let us also add 2D flows to this, and 2D we will be talking of two-dimensionality in the xy plane, or we will look at it in the polar coordinates in r theta. And if we have 2D flows, then we know that we can define a stream function psi, and this we can do. To define this, we only need the flow to be incompressible. And how did we define psi? Vx was equal to partial psi by partial y. Vy was equal to minus partial psi by partial x. This we have seen when we talked of the differential form of the continuity equation. Or alternatively, when I look at it in r theta coordinates, then Vr is equal to 1 over r partial psi by partial theta, and V theta is equal to minus partial psi by partial r. So this exists when the flow is incompressible and two-dimensional, and continuity equation is automatically satisfied. So for this, let's just write it again. Continuity equation is automatically satisfied. Now to this, we add the irrotationality part, which implies that del cross V must be 0. So now, when I look at del cross V, then I have partial Vy by partial x minus partial Vx by partial y must be 0. So when I do this, let's put this partial Vy by partial x gives me minus del square psi by partial x square minus del square psi by partial y square is equal to 0. So what we have is, for this class of flows, we also get del square psi is equal to 0, where psi is the stream function. Actually, in a general way, for 2D flows, you can see from here del square psi is equal to minus of omega z. So, and where omega z is the z component of vorticity. So for 2D incompressible potential flows, the governing equations we have seen del square phi is equal to 0 was already there, but we can also write it as del square psi is equal to 0. And these are equivalent equations. So we can either solve for phi or solve for psi. Now what is the big advantage, or why do we write it in terms of psi? What we have seen is that when you say psi is equal to constant, this gives us the equation of streamline. So therefore solving for psi makes it slightly better in terms of flow visualization. Now a line of phi is equal to constant, we can call it as an equipotential line. So we have streamlines and equipotential lines for the same flow. And the question we ask is, are they related? And to answer this, let us see on a streamline. Let's look at the equipotential line and a streamline. So what we see is on a streamline d psi is 0. This implies, if we look at it, that 0 is equal to partial psi by partial x dx plus partial psi by partial y dy. And from here what we get is dy by dx, or the slope of a streamline, is equal to minus partial psi by partial x divided by partial psi by partial y, and this will be equal to Vy upon Vx. This we have already seen. Now let us see what happens on an equipotential line. Equipotential line d phi is equal to 0, and this implies 0 is equal to partial phi by partial x dx plus partial phi by partial y dy. And from here what we get is dy by dx for equipotential line, this is equal to minus partial phi by partial x divided by partial phi by partial y, and this is equal to minus of Vx divided by Vy. And what we find is that slope of streamline multiplied by slope of equipotential line is equal to minus 1. And what does this mean? This implies that streamlines are orthogonal to equipotential lines. So that is the meaning of this. So if you have a streamline like this, if this is a streamline, then perpendicular to this at this location will be an equipotential line. Here the equipotential line at each of these points will be perpendicular to the streamline. So this is one this thing which we make. Secondly, and this is where you will now see how we relate these to actual flows. If we plot streamlines in a potential flow, so if this is a streamline, so each of these, let us say, represents streamline. Now what we know is that flow cannot cross a streamline. So this means that we can replace a streamline or a part of a streamline by a solid body. And the distribution of psi gives us flow around that body. So for example, here I have shown these streamlines. I can take a part of a streamline and replace it by a solid body, and it will make no difference. Now, of course, the question may come, what happens to the no-slip boundary condition? But then the no-slip boundary condition is irrelevant for this class of flows, because viscosity is neglected. And we have seen this in detail in the last lecture, that viscosity can be neglected. So therefore, what one tries to do is, we look at the flows and we plot different streamline patterns. That means now we have this equation del square psi is equal to 0. And we solve this 2D Laplacian equation for different flows. This is a very well studied equation in electrostatics. This equation has been well studied. For hydrodynamics, for fluid mechanics, this has been well studied. So there are libraries of solutions of this which are available. And the equation is the same. We get different size for different boundary conditions. So if we come across a flow situation where we think that the streamline matches a shape of a body, then we can just work on this. So now in this, let's see, a typical boundary condition we come across is boundary condition at infinity, where V infinity is known. Now V infinity would basically mean, so for example, if we have flow past a cylinder and V infinity is like this. Now we can, if we look at the boundary, if we look at velocity, Vx is equal to partial psi by partial y, and Vy is equal to minus partial psi by partial x. So here at infinity, what we have is, if Vx is equal to capital U, so the boundary condition will become partial psi by partial y is equal to capital U as r tends to infinity, and Vy is 0, so minus partial psi by partial x will become equal to 0. So this is the boundary condition we will get. For a general case, if velocity at infinity or far from the body is equal to ui plus capital Vj, so then what we will have is, in that case, partial psi by partial y is equal to capital U, and partial psi by partial x will be equal to minus of capital V as r tends to infinity. So this will be the boundary condition which we will use. Now this is one case. Secondly, if there is a body on a body, so for example, if we have this cylinder somewhere in the flow, in a 2D this is a cylinder which will be a circle. Now on a body, what type of boundary condition do we have on streamline? Now clearly, as we have seen, psi is equal to constant for any streamline, and since the body represents a streamline as we have discussed, so on a solid body, the boundary condition will become psi is equal to constant. So this is what we have, and here if we write this boundary condition in terms of phi, then this will become partial phi by partial n is equal to 0. So psi is constant or phi. So that is how we can then work out the boundary conditions for either for psi is equal to constant, for phi it will become partial phi by partial n is equal to 0. Here also you can work this out. It will become, if we write it in terms of phi, then partial phi by partial x will become equal to u, and partial phi by partial y will become equal to v as r tends to infinity. So boundary conditions can be written either for psi or for phi. Now there is one more thing which we need to know before we start looking at some flows and some standard phis and psis, and this is what we call a stagnation point in a flow. In a flow, a stagnation point is a point what do we expect? This should be a point where velocity is equal to 0. So this would mean that on this point, Vx will be 0 and at the same time Vy is 0, or Vr is equal to 0 and V theta is equal to 0. Now, the importance of stagnation point is that this will often, it will help us to identify a solid body kept in a uniform flow. And let me just illustrate. Suppose if I have a cylinder like this and there is uniform flow. So I'm talking of a physical situation, cylinder in uniform flow. Then what we know is, as the flow approaches the cylinder, then the point on the nose of the body is the one where typically V is equal to 0, and such points are stagnation point. So if we follow a streamline which comes here, it hits the nose of the body, and that is the stagnation point. And often what we find is that streamline passing through stagnation point often will give us a solid body of some particular shape. So our methodology will be, we first find phi or psi, then we locate the stagnation point, and after we locate the stagnation point, we find the equation of psi passing through stagnation point. And this will not always, may give us some shape of a closed or open body, and which may be of interest. So this is how, in a nutshell, we will be trying to solve problems. And then other thing which will happen is, once we find this, then what we will try to do is, we will then try to find flow pattern around the body, and then we may try to find the drag force or the lift force. But one word of caution, when we try to find these forces, we do realize that we are talking of inviscid flows, and viscosity effects have been neglected. And this will lead to some important consequences, and we will have a look at them. Now, there are two theorems which I will not prove, but you should keep them in mind. And actually, they both go by the same name, and this is called Blasius theorems. And they are easy to prove once we are doing the general theory of these using complex variables. What Blasius theorem tells us is that for this class of flows, for inviscid, irrotational, incompressible flows, what it says is if we have a body placed in uniform flow. So let's first understand this. There is at infinity we have uniform flow, and there is a solid body placed in uniform flow. So once again, the example would be the same. Suppose we have a cylinder, we have this uniform flow. That means you look at one of the streamlines, it turns out to be a closed circle. The streamline may be just a part of the streamline. It need not be the full streamline. So if we have a pattern like this, and this shape could be anything, it need not be cylinder. So this is any closed body. So I'm shown here as a cylinder. I've shown it could even be an elliptical shape with uniform flow. So what Blasius theorems, the first theorem says is that the drag force on this body is equal to 0. This can be proved. For inviscid irrotational flows, a drag force on a closed body kept in uniform flow will be 0. And the second one is the lift force. So drag force is basically force in direction which is parallel to the velocity at infinity. Lift force is force in direction perpendicular to velocity at infinity, and lift force is given by minus rho u, where u is the infinity velocity, times gamma. Now here gamma is the circulation calculated along the closed body. Remember, we had said gamma was equal to integral Vt dotted with ds on any closed curve. So since a closed body is a curve, you calculate circulation along the closed body. If circulation is 0, then the lift force will also be 0. If it is non-zero, then lift force will be equal to minus rho u infinity gamma. And we will show this. No, so now, how could these, we say that these are inviscid flows. So how can we get drag force or lift force? Now, drag is 0, notice, only for a closed body. If the body is open, the drag could be non-zero. And these come because of pressure. The drag and lift force will come because of pressure. So suppose if this is a body, let's say this is an open body, I choose an elemental area dA, I have pressure acting there. So if I look at integral, so if pressure is acting like this, if this angle is theta, integral P dA, and this is how the velocity at infinity looks like, integral P dA cos theta, this will give me the lift force, and integral P dA sine theta on the body integrated around the body, this will give me the drag force. So in these flows, the drag and lift and all these forces come only because of pressure. In a general flow, they will come also because of viscosity. And sometimes this component of drag due to pressure is also called pressure drag or form drag. This will be in a general case. When we also have viscosity, then the component due to pressure is called the form drag or pressure drag, and the component due to viscosity, this is called the skin friction drag. Okay. So now, having seen all this, let us try to now look at some standard flows. So now we will look at a library of solutions, some standard solutions for phi or psi, where del square phi is equal to 0 or del square psi is equal to 0. Now we are looking for the solution of del square phi is equal to 0 in a general way. Let us look at the equation. This is Laplace's equation. In Cartesian coordinates, this looks like d2 phi by dx square plus d2 phi by dy square is equal to 0. And in cylindrical coordinates, you can check this. This looks like 1 over r d by dr of r partial phi by partial r plus 1 over r square partial phi by partial theta square is equal to 0. These are the two versions. So clearly, if phi is of the form ax plus by, then del square phi will be 0. This is one of the simplest forms we can think. Also, let's try to think in cylindrical coordinates. If we have d by dr of r d phi by dr, if this is equal to constant, that means r d phi by dr will be equal to, d phi by dr will be equal to k by r, and phi is equal to k log r. This will satisfy. So if phi is of this form, this will satisfy Laplace's equation. Another form we have is d2 phi by d theta square must be 0. So if we are looking at functions of theta, if phi is equal to a theta, then also we know this will satisfy Laplace's equation. So this gives us some basic idea of the type of flows which will satisfy del square phi is equal to 0. So given this, now let's start. So the first flow we will look at is when phi is given by capital U times x cos alpha plus y sin alpha. So here U and alpha are constants. So here if we look at this, partial phi by partial x is equal to U cos alpha, and partial phi by partial y, this is equal to U sin alpha. So that means this is Vx and this is Vy. So this is a uniform flow where so these are Vx and Vy. So because I know this is the form of Vx and Vy, the streamlines are going to look like this. So therefore, in this flow, so here what we have, this is angle alpha and Vx. So this is flow where the velocity is equal to capital U at an angle alpha from the x-axis. So this is uniform flow, and for this, if we now try to work out the streamlines, and this I'm showing as a general procedure. We have what we know is Vx for this is given as U cos alpha, capital U cos alpha, and this is also equal to partial psi by partial y. So therefore psi will be equal to U cos alpha times y plus function of x. We are doing it in a general case, and then we differentiate this, so we get partial psi by partial x. This will be U cos alpha times, sorry, this was y. We have integrated with respect to y. So psi is equal to U cos alpha y plus function of x. And now we differentiate this. So partial psi by partial x is equal to f prime of x. And this we know is equal to minus d psi by dx is minus vy. Now vy is what? U sin alpha. So this is equal to minus of U sin alpha. And therefore, if we now integrate this, we will get psi is equal to, or this is f prime of x, sorry, is equal to minus U sin alpha. So integrate this, we get f of x is equal to minus ux sin alpha plus a constant. And since things are up to one arbitrary constant, we can choose this to be 0. So therefore what we get is the stream function for this flow is equal to U cos alpha y minus U sin alpha times x. So this is the corresponding stream function. And by doing this simple exercise, I have also shown you how do we find the, if you are given phi, how can you find psi? Or if you are given psi, how can you find y? How can you find phi? Now normally in most of these cases, alpha will be either 0. This is what we have seen when we have uniform flow like this. And for this, therefore, this flow phi will be equal to ux and psi will be equal to uy. So this is how we have. Now, so this is one basic flow. For the second basic flow, let us now look at the 2D polar coordinates, and as we have just seen that both ln r and theta satisfy Laplace's equation. So therefore let us look at the first one, and that is what we will call as the number 2 here. So let's look at the first equation. So which we will now, so we'll use this log r as the second case, and this we call a line source or sink at the origin. So let z-axis be a porous pipe through which flow oozes out at a rate capital Q per unit length B of the pipe. So think of a pipe, a very thin pipe through which it's a porous pipe through which flow is oozing out in a radial direction from all its surface. So we are shown only the top and bottom surface all around. So if I look at the side view of this pipe, I look at a very small section and flow is oozing out radially in all directions at a rate Q per unit length of the pipe. So we are looking at this view. So this is the z-axis and we are looking at the xy section. So here that means if I look at this, there's a pipe, there's a point here from where flow is coming out in the radial direction. So now if I look at this, look at a situation where the radial component of velocity, it goes like 1 over r and v theta is equal to 0. So if this is the situation which is given to us, because this Vr is equal to m over r will come from the continuity equation. If we apply the divergence free condition, we will get Vr is equal to a constant by r. So now if Vr is equal to m over r, let's try to see what the psi looks like. This will be equal to 1 over r partial psi by partial theta by definition of Vr. And from here what we will get is psi for this flow is equal to m theta. And we can show this is what the general form will be. And if we also use Vr is equal to partial phi by partial r, and this is equal to m over r, from here what we will get is, when we look at this, that phi is equal to m ln of r. So therefore this flow, if we have psi and phi in the form, if psi is equal to m theta and the corresponding phi is equal to m log r, and m, if we try to put it in terms of the physical flow rate, it will be equal to q dot by 2 pi b, where b is the length in the z direction. So this flow will also satisfy the potential flow condition, because del square psi and del square phi is equal to 0, as we have seen that log r and theta satisfy this. Now in this flow, if m is greater than 0, then the flow is leaving the pipe. Vr is greater than 0, and this is what we call as a source, or we'll call it as a line source. And if m is less than 0, then the flow is coming toward the center, and this is what we call as a sink. So this is the second type of basic flow which we have, where we have a radial flow. Now the third basic flow which will come, and which you can sort of expect from here, if we interchange psi and phi here. That means if phi is of the form of theta, m theta, and psi is of the form log r. And if we look at this gives us a flow which is called a line irrotational vortex. And this is a flow where v theta is equal to k by r and Vr is equal to 0. That means if you look at this, all streamlines in this flow are circular. In the previous case, the streamlines were radial. So here if the streamlines are circular, which means this will be the type of streamlines we will have in the flow. So if we put v theta is equal to k by r and we work out, then phi will turn out to be equal to k times theta, and psi will turn out to be equal to minus k log r, and this is for a counterclockwise direction of v theta. So these are the expressions for phi and psi. And if k is greater than 0, then we have a counterclockwise vortex, that is what I had just indicated here. And if k is less than 0, then we will have a clockwise vortex. Now, this flow is called a vortex flow because we have circular streamlines. But we notice that this flow is irrotational. The flow is irrotational. That means if you put as we have said, that omega or vorticity for this flow will turn out to be 0. Now, one thing which we will be able to show is that, so here basically once again the vortex has been placed at the origin, and in the sink flow again the source or sink was placed at the origin. Now one thing to be observed is in both 2 and 3, origin is a singular point. And what do we mean by this? That at r is equal to 0, either the incompressibility or irrotationality condition is not satisfied. That means what we are saying is, if we look at the source or sink flow at r is equal to 0, the flow is either being created or it is being sucked in. So therefore there is some sort of a mass generation taking place at r is equal to 0. But at all other points in the flow, del dot v is equal to 0. We can't say this only for the origin. And similarly for the irrotational vortex, the vorticity is equal to 0 at all points except the location of the vortex, that is at r is equal to 0. And a consequence, so that means in this irrotational vortex there is sort of concentrated omega at r is equal to 0. And this one has a particular significance. If I calculate circulation around any closed curve in this vortex flow, then what I will find is, if the curve does not enclose origin, then circulation is 0. So that means I choose a curve like this, I choose some closed curve, I choose these curves A, B, C, D. On these, if I calculate circulation, which is equal to integral Vt dot ds, this will be 0. And this is easy to see from, we had shown, this is easy to see from Green's theorem, because this is also equal to integral of omega, what was it, omega cross n dA. We had shown this, and so no, it was integral, sorry, it was integral omega dA. And because in all these curves omega is 0 throughout the domain, circulation is 0. But if we choose a curve like a closed curve like this, which encloses like this, which encloses origin, then circulation in this curve, around this curve, is not equal to 0, because omega is not 0 at origin. In fact, it is tending to infinity. So when we calculate around this, we will get a non-zero circulation. And actually, as if you may put 2 and 2 together, when we did Blasius theorem, what we said was that we had the lift was given by rho u times gamma. So that means in flows, if we have a closed body which encloses an irrotational vortex, lift may not be zero. Okay. So now we have seen these three basic flows. Now what do we do with these basic flows? With these three basic flows, we can build solutions. And how do we build solutions from these basic flows? Well, we build them because we know now we can superpose different solutions. We have seen this because these are linear flows. If phi1 is a solution with boundary condition BC1, and if phi2 is also a solution with boundary condition BC2, then phi1 plus phi2 with boundary condition BC1 plus BC2 is also a solution. And this is what we do. We have these three basic flows. We try to combine them and we try to find solutions, and we try to see if there is some interesting flow which comes around. And let's look at the first example in this class. More examples will follow. And the first example which we do is uniform flow plus source at the origin. And you can try and visualize these things by drawing this flow. So uniform flow, let's take it like this. And let this be our axis. And there is source at the origin. So we have we superpose these two flows. And how do we superpose? Our phi for uniform flow is ux, and phi for the source at origin is m log r. So this is for uniform flow, and this is for source at origin. So the superposed flow, the phi will be given by this. And similarly, I can write psi for this flow. Psi will be equal to uy plus m theta. So this is the equations which we have. So now let's try to find the stagnation point. As we said, stagnation points and streamline passing through stagnation points may give us something interesting. So to find the stagnation point, what we have is, let's write this phi. Phi which we have written, we either write in terms of xy or r theta. So we write phi is equal to x, I write it in terms of r cos theta plus m log r. So this is phi. Now for stagnation point, let's first put Vr is equal to 0. That means we will put partial phi by partial r is equal to 0. So it gives me u cos theta plus m by r is equal to 0. Second, we put v theta is equal to 0. V theta is 1 over r partial phi by partial theta is equal to 0, and this will imply minus u times sine theta is equal to 0. So that means if I look at for v theta to be 0 implies sine theta is equal to 0, which will imply either theta is equal to 0 or theta is equal to pi. Now we feed this in expression for Vr. We put this in the expression for Vr. So therefore we will get u cosine of pi or cosine of 0, so there will be two equations, plus m log r is equal to 0. M we know is positive because we are talking of this. So now what we get is, if we put theta is equal to 0, then we will get r is equal to, so theta, so we put it in expression for VR. Sorry, I have made a mistake here. M log r, I just copied from here. It is m by r. For stagnation point, I have to put m by r, not log r, because I have to take the derivative. I missed that. So for here, what we will get is, if I put this is equal to 0, u is equal to minus m by r, or r is equal to minus m over u, and this is for theta is equal to 0. For theta is equal to pi, what we will get is u times minus 1 is equal to m by r, or r is equal to m by u. Now obviously case 1 is not feasible because r is always greater than or equal to 0. That means the stagnation point occurs at theta is equal to pi and r is equal to m by u. So if I look at this figure, stagnation point is going to occur somewhere when theta is equal to pi, somewhere at this location where r is equal to m over u. At this distance, we will get the stagnation point. And the reason I have come back to this figure is, if you try to now look at this geometry, it is sort of obvious that this could be a stagnation point, because on this uniform flow, the effect of this is a positive velocity everywhere in the flow domain. On the x-axis, we have, on the negative x-axis, the velocity is negative. So there will be some point where these two will be balanced and will cancel out, and that gives us the stagnation point. So from a geometric viewpoint also, this stagnation point looks feasible. So this is our stagnation point. Next, what we try to find is the streamline passing through the stagnation point. So stagnation point, as we have seen, was given by r is equal to m by. Now the equation of streamline is uy plus m theta. So let's write the general equation. Psi is equal to uy plus m theta. So now we feed in, or we first write u times r sine theta plus m theta. So here we feed theta is equal to pi and r is equal to, what was the value of r? R was equal to m by u. So when we feed this in here, what we get is the value of that psi. So sine theta will give me 0. So first I get a 0 plus m pi. So this is the value of psi for the stagnation streamline. Okay. So this is the value, psi is equal to m pi. That means the stagnation streamline is given by, this is given by u times r sine theta plus m theta is equal to m pi. So this is the streamline which passes through the stagnation point. Now let us try to see if this makes any, how does the streamline look like, and you can do a plot. Now for you it's very easy. You can even take an Excel sheet, plot different values of theta starting from 0 and go to different values get to different values, and what you for different values of r, and what you will find is obviously this point is there where r is equal to m by u. It has to pass through this point, and the stagnation streamline looks like this. This is the stagnation streamline, and this is like what we call an open body. This streamline does not close. If we look at this streamline, the streamline does not close at infinity. And this is what we call as a Rankine half body. That's the name given to this. So if you have line source at origin plus uniform flow at infinity, here we get a flow past what we can call is a Rankine half body. Now on the surface S, we can find Vr and V theta on the, so let me call this surface of this body as S. Vr and V theta on surface S can be found. Notice in general, Vr and V theta will not be zero. What is zero will be the normal component of velocity to S. Velocity normal to S will be zero, and this comes because it's a streamline. But in general, Vr, V theta on S will not be zero. So now what we can also do is we can use Bernoulli equation to find pressure on the surface S. So we use Bernoulli equation between infinity and a point on S, and what we will get is, when we use Bernoulli equation, P infinity plus half rho capital U square. This will be equal to pressure on the surface plus half rho times Vx square plus Vy square on S, or we can use plus half rho Vr square plus V theta square on S. So using this we can find pressure on the surface. And once we can find pressure on the surface, then we can integrate this on the half body to get drag on this half body. Now, what is the significance? Is there any physical significance of this flow, or any implications in real life? Where could this happen? And suppose if we think of this origin, so let's look at this. Let me draw this again. So this is how this flow was. Suppose we have a river which is flowing, and there's a river which is flowing, and there's a pipe which is, let me get back to the pen. Somehow it seems to have stopped working, but we'll get back. So let's get back to the figure. So we have this flow here, and we have, if so in this flow, what we had, let me just try to get back the pen on. So on this, So I'll get back to this. Just sorry about this small interruption. So we are talking about the physical impact of this. So suppose pollutants laid in water is being released at the origin, and this is flow of a river. So this is the river which is flowing and pollutants are being released from this point. Then what we know is, because there is a streamline like this, so the pollutants which get released, they will not be able to, these pollutants will not be able to cross the half body. So we know the extent of the half body, and we can say that all pollutants will be confined to this half body shape which is there. So therefore, this tells us the extent of spread of pollutants will be given by the half body. So that is what it is, and this is where so this extent is given by the half body. I think we will end at this point, and we will talk more about different flows in the next class. Thank you very much.